Hi, welcome to Putting Too Much Confidence into Anecdotal Evidence. Here's something humans do. A person will say to their friend something like, "This sandwich has been in the fridge for a week. Do you think it's still safe to eat?" And their friend might answer something like, "A few days ago, I ate a week-old sandwich. I was fine." Or they might ask their friend, "I'm going to throw this new red shirt in the wash with my other laundry. Do you think that will be okay?" And their friend might answer, "I did that recently with a new shirt. It was fine." Or they might ask, "I'm thinking about buying this chair for my office, but the reviews say they sometimes show up damaged." And their friend responds, "I bought one of those. It was fine." There is a hidden assumption in these questions, and that assumption is that the same action always leads to the same result. But reality often does not work this way. Often it is more realistic to say that the same action can lead to many different possible results, and each of those possible results has a probability of happening. Here we denote those probabilities as P1, P2, etc. So when we ask our friend a question like whether or not it is safe to eat a week-old sandwich, and they say they did it and were fine, we're acting like either that the probability is 100% that we'll get sick and 0 that we won't get sick, or that the probability is 0 that we'll get sick and 100% that we won't. And that their good outcome implies that the latter case describes reality. Instead, it's more reasonable to say that the bad and good outcomes each have a probability, here called P1 and P2, and that your friend's good outcome tells us something about the values of P1 and P2. This is not exactly like the data analysis we usually look at on this channel. When we ask our friend these questions, we do get some data on which we base our decisions, but often not very much. So when we ask these questions, what sizes of probabilities are we sensitive to? In other words, what we're asking here is, when your friend says, "I was fine," how much does that actually say about P1 and P2? Now, usually on this channel, we look at tools for analyzing scientific data. So we're going to use those tools here and look at this everyday ask a friend practice from a data analysis standpoint. We want to get a good feel for what this practice tells us and what it doesn't. We'll see how much we could improve if we use data analysis tools in real life. In other words, by looking at this practice from a data analysis standpoint, it will be clear that we can do better than this. This video is somewhat related to another video I have on this channel called "A Conversation I Once Had with a Kid on a Plane," which is about a real conversation I had with a kid on a plane about the risks of using a cell phone on a plane. I explained to him why his reasoning wasn't statistically sound. So as long as we're drawing conclusions from anecdotal evidence, I guess we could say that this shows how much fun it is to sit next to me on a plane. Okay, now let's look at some scenarios. In each of the imaginary situations above, there were two generic outcomes, one good and one bad. We don't know the probability of each of these two outcomes. So, since we don't know, let's consider a bunch of hypothetical cases. Each scenario we consider will have different hypotheses for the outcomes. Specifically, each scenario will have different probabilities for the good and bad outcomes. In each case, we're going to ask the following. Is your friend's saying "I was fine" compatible with this hypothesis? Now, what compatible means is a matter of judgment. What we will do is ask, if the hypothesis is true, is your friends saying they were fine very unlikely? If, under the hypothesis, your friends saying they were fine is very unlikely, we will consider the hypothesis incompatible with data, or incompatible with observation. Here, the data or observation is just the fact that your friend was fine. Exactly how unlikely your friend's positive outcome has to be to rule out the hypothesis is a choice we make, which we will come back to in a bit. Now, we should mention that when we say a hypothesis is not compatible with data or with observation, that does not mean the hypothesis is impossible or known to be false. It means that the observed result is sufficiently atypical under that hypothesis that the hypothesis is deemed incompatible with the data by a standard that we have previously decided upon. We should also note here that we are assuming there's nothing about your friend or you that would make either their experience or yours special. We're assuming you don't have any information to indicate that your friend's situation is systematically different from your own. Okay, so here's the table of scenarios that we're going to consider, which we've numbered from 1 to 7. Each one of them has a probability for a good outcome and a probability for a bad outcome. We're assuming that we can group all possible outcomes into one or the other of these generic classes. We've ordered them according to these probabilities. At the top, we have the scenarios where the bad outcome is very likely, and at the bottom, we have the scenarios where the good outcome is very likely. Now, which of these hypotheses are incompatible with your friends saying that they were fine? Well, in the last 3 scenarios, the good outcome is more likely than the bad outcome. And in scenario 4, the good outcome and the bad outcome are equally likely. Clearly, your friend saying they were fine doesn't rule out any of these scenarios, as your friend's outcome is typical in these cases. So that leaves us with scenarios 1 through 3. In all of these cases, your friend would usually report a bad outcome. Are these hypotheses compatible or incompatible with the data? So to figure this out, we ask, under each hypothesis, is your friend saying they were fine very unlikely? Let's first look at scenario 3. Under this hypothesis, your friend's positive outcome had a 20% chance of occurring. This outcome is somewhat unlikely, but it's hard to say that it's very unlikely. In scenarios 1 and 2, however, your friend's good outcome has a pretty small probability, 0.1% and 1% respectively. A lot of people would consider your friend's good outcome as very unlikely under these scenarios. This is a matter of judgment, which we'll come back to in a minute, but for the moment, let's say we take the probabilities of these scenarios, which are 1% or lower, as very unlikely. And we should note that, to avoid bias, this decision should be made before you know about your friend's experience. Okay, so out of the original table of scenarios, we were only able to rule out the first 2 from your friends reporting a good outcome. In fact, we were only able to rule out those scenarios where a bad outcome was a near certainty. Meanwhile, other scenarios where a bad outcome is common are compatible with the data. When we take our friend's good outcome as indication things will be okay, we're acting as if these cases don't exist. And while we're at it, even scenarios 6 and 7, where the bad outcome was least likely, may not be acceptably low risk, depending on the context. For very important decisions, a 1% or even 0.1% probability of a bad outcome may not be okay. Just to make this a bit more concrete, if a company sold products that turned out to be defective 90% of the time, you probably wouldn't want to buy from them. But if your friend buys a product and reports that it was fine, you haven't ruled out this scenario. An "I was fine" from your friend gives us remarkably little information. It doesn't rule out important cases where the probability of a bad outcome is not that small. Depending on the context, one might be taking big risks by making decisions this way. And yet, people do this all the time. With some data analysis skills, we can have a better idea of what information we have and what information we don't have. So let's put what we did here in those terms. Okay, what did we do here? We did a rudimentary form of hypothesis testing. We rejected those hypotheses for which a result as strange or stranger than what we actually observed was very unlikely. For the scenarios in which a bad result was a near certainty, your friend's good outcome was very strange. We thus rejected those scenarios where a good outcome from your friend was rare. In other words, we rejected hypotheses for which the observed p-value was small. Here, small means smaller than some pre-decided value, which is called the significance level and is usually denoted alpha. Here, we didn't do this formally. Alpha should be decided ahead of time, but we can look back and see what we did. We ruled out scenario 2, where only 1% of results would produce a good outcome, like that reported by your friend. But we did not rule out scenario 3, where 20% of results would produce a good outcome. This is what would have happened if we had chosen a value for alpha, which was at least 0.01, but less than 0.2. A common value chosen in many fields is 0.05, but there are also certain cases, like possible particle physics discoveries, where much, much smaller values are used. Okay, time to summarize. The main takeaway from our example is that when we put this in terms of hypothesis testing, we can see just how poor this Ask a Friend practice is at ruling out a wide range of important hypotheses. More generally, understanding statistical tools can show us how much we can improve on everyday practices for understanding the world around us. For example, we could try to get a larger statistical sample than just one friend. If you'd like more information on hypothesis testing, I'd suggest you check out the hypothesis testing playlist available on this channel. It contains information on p-values, statistical significance, confidence intervals, frequentist and Bayesian statistics, etc.